All right. Hello. Let's start this, I guess, the first actual lecture in this course. And we're going to look at just the basics of complex numbers, definition of the complex numbers. We're looking at subsection 1.1.1. Now, modern mathematics, a lot of times what it does is something that you wouldn't think of maybe as the obvious thing to do, but we take a false statement, something that isn't true, like all polynomials have a root, and instead of figuring out which polynomials have a root, we change what it means to have a root, and we change it so that this statement is correct, right? It's actually exactly what we do in definition of complex numbers. So let's look at some examples. You start with the natural numbers. And we get the integers by basically saying, well, we want to solve equations like this, right? Let's say n plus 2 equals 1, right? So you need minus 1 for that, right? I mean, in some sense, all you're saying is minus 1 instead of a placeholder that will, that will solve this equation. All right, well, you could go further. You could look at some equation like 2x equals 1. Well, that's not possible to solve with z, but we could get the rational numbers by basically saying, well, I want to solve these guys. For example, the solution here is 1/2. How do we write 1/2? 1 divided by 2. Did we really solve anything, or did we just make up a new concept, right? Now, we could start with the rational numbers, and well, we can't always take limits, but well, if we want to end up in Q, but well, if we throw in all the possible limits, we get the real numbers, right? So now we can take sort of limits willy-nilly. So, so let's go further. Suppose that I have this guy over here, z squared plus 1 equals 0. I want to solve that, right? I'm basically back to this statement, all polynomials have a root. I want this guy to have a root. Well, that's how you get the complex numbers, right? The complex, the imaginary number is precisely the guy that solves this polynomial, right? That's a root. Now, interestingly, the analysis with complex numbers is quite different from analysis with the real numbers. The main difference is that in complex analysis, basically, we look at what happens when you ask for the complex derivative, and you'll see more of what that means. And interestingly, you get all sorts of weird statements. So, for example, right, a couple of examples. If you can differentiate once, if you have a function that's once differentiable, you can differentiate twice, right? Why should that be true? Every function kind of acts like a linear function. See that it's like, for example, there are no maxima. If all derivatives are 0 at a point, the function is constant. Okay, this one might not seem as as weird, but it's not true if you're just looking at even infinitely differentiable real functions. And we get lots of other similar statements. Now, the main difference between real analysis, when you go into graduate school, a lot of times you take two courses. You could take a real analysis course and you could take a complex analysis course. So the real analysis course is supposed to sort of crush your dreams. It's supposed to show you like all the stuff that's everything's false. Nothing quite works. You need all sorts of hypotheses to make something work, right? On the other hand, complex analysis course, things are too easy in some sense. There's too many things are true, so you kind of get overly optimistic about what could be true, right? So it's kind of yin and yang thing. I mean, they're both, I mean, related. They're both analysis. So, but that's kind of, I guess the main difference. All right, so let's get to complex numbers. In some sense, I'm gonna assume that you guys have seen complex numbers to some degree, but let's get to, let's just define it. So really, complex numbers we're really thinking of as a set. It's just R2. There's no difference as a set. The difference is that we add multiplication. And multiplication, we can just define it, right? Well, we have addition. Well, addition is that's still on R2, right? R2 is a vector space, so that's the regular addition, vector space addition. Now, the multiplication that I'm talking about is over here, right? And so we add this, and that's what we're going to call, if we're multiplying two complex numbers. It turns out this actually makes it a field, which is maybe a little bit surprising, but yeah, that's what it is. Now, we can think of R as a subset of C if we identify any real number with the basically with the horizontal axis. That's x0, right? So when the y coordinate is 0, that's what we're gonna call a real number. Sometimes called the real axis, right? We get the imaginary unit I, right, which is just 0, 1, right? Now, this I has this magical property that if you plug it into this definition, if you square it, right, so multiply I with itself, you get -1. So yeah, now I can solve this this polynomial, right? There's two solutions, I and -I. Now, another way of getting at the complex numbers is not maybe to define it this explicitly, but to start with R as a ring, as a field, and adjoin the a root of this guy, right? And you get this, everything's the same. So that's just more algebraic version, right? There's really two roots. In some sense, you're picking an orientation, and either you pick this one or that one, but really underneath they're kind of the same thing. It's just that we write either everything in terms of one or everything in terms of the other. So we just pick one. We're calling that I, and the other one is -I, right? If we pick the other one to be I, then everything would be the same. You wouldn't be able to tell the difference. All right. So from now on, when we write xy, it's well, we're not going to write it. It's when we have xy, we'll write it as x plus iy, because 1 and I are actually the basis on. It's actually the standard basis for R2, so we can just write complex numbers as x plus iy. It's usually called the Cartesian form of the complex number. So we're going to just do that from now on. Now we're going to write x comma y, really. Now, as I said, there's two roots to that polynomial. So everything can be flipped over. We can look at the other orientation. We can look at the world in the mirror, right? And I mean, in some sense, it's the same world. And we can't tell the difference, which one we're in, really. But, when we're in one, we can mirror, we can be, we can look what it would look like if it was mirrored, right? And that's this complex conjugation, right? So we basically swap the swap the roots, right? So if I have of that polynomial, so if I have x plus iy, we get x minus iy. So that's the complex conjugate, right? Now let's give some names to the x and y. We call it the real part, which is just the x. Now you can actually, once you have the complex conjugate, you can actually write down an expression, z plus z bar over 2 actually gives you x, right? So you could just write that. So that's the real part, the x. Imaginary part is the y. And again, I can write it as a, in terms of, an expression in Z and Z bar, right? So that's the imaginary part, right? Maybe something just to, some, the imaginary part is the Y, not the IY, right? That seems to be a somewhat common mistake of some beginning students. So just the Y, just the real part that's the coefficient of the Y. All right, now if I have an arbitrary expression, well, nice one, let's say polynomial, in X and Y, I can plug in these expressions in Z and Z bar and get an expression in Z and Z bar, and I could expand this if I wanted to, right? So this thing in terms of X and Y is something in terms of Z and Z bar, right? Or maybe even vice versa, right? I mean, if I have something in terms of Z and Z bar, I have something in terms of X and Y, right? It's the same thing, right? So in some sense, it almost looks like Z and Z bar could be, separate variables, independent variables. And to some degree, it actually works like that. So, all right, that's it for right now. And so next time, we're gonna look at a little bit more of the geometry and the topology of the complex numbers and the and complex valued functions, and just the very, very, very basic analysis that one does with them.